integer representation.
Yeah, my main questions were how you actually wanted us to write the binary signed representations and all that, because there's a few different ways to do it.
Okay, for the signed integer representation today?
Yeah, but
Yeah, we can look at them.
Yeah, because we haven't even gotten there yet, but once we do, I'll have a question.
All right, awesome. Now, the conversions we have so far presented have involved only unsigned numbers. That means positive numbers only. Now, to represent signed numbers inside of a computer, there's a couple different ways that people have thought to represent signed integer representation, but the signed integer representation that computers implemented is 2's complement. But in order to understand 2's complement, they have us look at all the different ways that you can represent a signed integer inside, a numbering system. Okay? So to represent signed integers, computer systems allocate what's called a high order bit to indicate the sign of a number. And if you took C++ with me, sometimes we looked at our numbers. And when we spit out our numbers, we notice that the first bit, so that first 1 or 0, if it was a 1, then it was negative, and if it was a 0, then it was positive. And then the remaining bits contain the value of the number. Okay, and that's what signed integer representation means. It means we use one bit to represent if it's negative or positive. So there are 3 ways which we can use signed binary numbers. Signed magnitude, 1's complement, and 2's complement. The way your computer implements it is with 2's complement. But like I said before, we have to look at these other 2 ways, kind of understand what 2's complement is. All right. So in an 8-bit word, signed magnitude representation places the absolute value of the number in the 7th bit to the right of the signed bit. Or 7 bits to the right of the signed bit. All right, so here's an example. So here's an 8-bit number, so that means it uses 8 ones or zeros. And it's using signed magnitude. So we all know how to write the number 3, right? This is our 2's place, this is our 1's place, so that's the number 3. And so positive 3 would have a 0 in our signed bit, and then negative 3 would have a 1 in our signed bit. Pretty easy to figure that out, right? All right. Binary addition is as easy as it gets. So when we're adding binary numbers, you only have to know 4 things because we're only working with 2 digits. You just have to know that 0 plus 0 is 0. What is 1 plus 1? 1. 0 plus 1 is 1. And what is 1 plus 1? Not 10. What is that number?
2.
2. Okay, we should all know 1 plus 1 is 2. But remember, that's in binary, so that's the number 2. Okay, not the number 10. Don't ever say 10 because this is the number 2. The simplicity of the system makes it possible for our digital circuits to carry out arithmetic operations. So I know it might be kind of hard to see now, but one of the reasons that they went with binary implementation inside of a computer because it was the easiest to implement in hardware. And then all of our abstraction comes through software. So they implemented at the easiest level, the hardware level, this binary numbering system. Okay.
One
Yes,
thing
Adam.
I've always wondered is how did they know that you could build any sort of logic out of just yes and no's? Like,
Okay, very good question. How did they know that you could build any sort of logic out of yes and no, or 1 and 0? And actually, they didn't know at first, right? And That's why Alan Turing's ideas were so radical. That
Oh, so
he
it
actually
was Alan
thought
Turing.
that you could build something other than just a calculator. When they're first implementing these computers, they just wanted a calculator. And they did implement it with the decimal number system. ENIAC was used in the decimal number system. And then they figured out how very hard it was to implement something like that in hardware. And they said, wow, if we had a simpler numbering system that we could implement in hardware, it'd be much easier at the hardware level. And the numbers are numbers, right? The number 1 is the number 1, the number 5 is the number 5. It doesn't matter what numbering system.
Uh-huh.
So they thought, oh, okay, we'll do binary because it's easier to implement in the hardware.
Okay.
And so they started with binary and they started making calculators, and then it was radical thinkers like Alan Turing and different people who said, well, we could implement our logic up here, our high level logic, and we could use Boolean algebra and break it down into its smallest parts, and we could break down our logic into binary. And then they figured out, oh yes, so when we build these layers of abstraction through software, now we can take these great ideas and have them implemented through a computer.
So it was.
So it did take a little while. It wasn't like at first they decided, oh, we're going to have Twitter on a computer. That was a totally radical idea, right?
So it was Alan Turing, and then I guess Boolean algebra was where we knew that we could implement like logic gates.
Yes.
Okay.
You know, it was Boolean algebra that we figured out, hey, this is the easiest way to implement this in hardware. This is probably the best way to do this.
Ooh. Okay.
Okay? So yes. And with signed numbers too, it was so much easier just to represent a positive number. How are we going to represent these negative numbers? And they represented it through 2's complements. So good question. All right. So here we are, we're presented with a problem that looks like this. And in our example, it's using signed magnitude binary arithmetic and find the sum of 75 plus 46. Okay, so this is the number 46, and let's see here, is the number 46? Oh, and here's our signed bits out here. So this is our 75, and then this is our 46. And you can see that this is the 2's place, right? 4, 8, 16, 32, that's 64 plus 8 plus 3. And so that would be your 75, right? Starting to be able to convert these in your head a little bit. Here's our 2, 4, 8 plus 32, that's our 46. So it says first convert the 75 and 46 to binary, which they did for us, and arrange as a sum. But they took these 8th bits, your signed bits, and they put them out here to the left. And then you just add, just like you normally add. So what's 1 plus 0? 1. What's 1 plus 1? 2. So you write down the 0 place and you carry the 1's place. So remember that with the 2. That's the only semi-hard part in binary arithmetic. And then you add and you'll get 2 again. And then what's 1 plus 1 plus 1? 3. But how do you write a 3 in binary? A 1 and a 1. So you write down your 1's place and you carry your 2's place. See how we're adding here? And then we just add down again. And we get a number that looks like this at the end. And what number does this represent? 75 plus 46, what's the answer? What is the answer? Was it 121 or something like that? Yeah. So this would be 121. If you converted this back to decimal, this is 121. Okay? And then you add up your sign bits so we know that this is a positive number. In this example, they were careful to pick 2 values whose sum would fit into 7 bits. If that's not the case, then we have a problem. Okay. All right, so of course they're going to tackle this problem, right? Well, what if, using signed magnitude arithmetic, find the sum of 107 and 46? Okay. So they add up 107, so this is 107, this is the number 46, and they add it up, and there's a carry at the end that's going to carry over into the sign bit. But what happens when we put this into the sign bit?
That would make it negative.
Yeah, it makes it negative. Okay, and it gives us the wrong answer because now we think the answer is 25. Because this number here at the end is 25. It's 16 plus 8 plus 1. So the signs inside magnitude representation work just like the signs in pencil and paper arithmetic. Oh, they don't tell you how they get rid of this. There's a technique that they use to get rid of this bit, this overflow bit. Okay, but they didn't go over that in this slide here. Okay. So they just say, hey, your overflow is discarded, and then you get the wrong answer. So there has to be another technique for utilizing or changing this sign bit, right? Or this overflow bit. So the signs inside magnitude representation work just like the signs in pencil and paper arithmetic. And if we're adding up two negative numbers, we add them and then we see that the sign at the end is negative. So here they're talking about how you can borrow. Okay, now why would you need to borrow here? Because the bottom number is a negative number. And so they're actually subtracting this number from the top number. All right. So sign magnitude representation's pretty easy for people to understand, but it requires complicated computer hardware. So you could see that, you know, in the early days, they said, oh, maybe we could use sign magnitude. They tried to implement in hardware, but then they had to do this borrowing thing. To tell you the truth, I gave you guys no homework problems on borrowing. That's why I kind of glanced through this slide. But the borrowing actually is really complicated in hardware. Okay? To get something to borrow is really hard to implement at the hardware level. So they decided that the signed integer representation wasn't a way that they were going to implement this in hardware. Okay. Another disadvantage of signed magnitude is that it allows two different representations for 0, positive 0 and negative 0. Okay. For these reasons, among others, computer systems employ complement systems for numeric value representation. So that's what we're going to look at now, is how to take a complement of a number and how we can use that to add a positive number and a negative number more easily than just borrowing. So in complement systems, negative values are represented by some difference between a number and its base. Okay, the diminished radix complement of a non-zero number and in base r with digits is that radix to the power of d minus 1 minus the number n. It's actually much simpler than this, so don't worry about that too much. So in other words, here's how we represent positive 3 in signed integer 8-bit 1's complement. This is the positive 3. And then this is negative 3. And what did you notice right here?
You just flip each.
Right, you just flipped it. So you actually did subtract it, right? But you can just think, okay, all my 1's became 0's and all my 0's became 1's. Pretty much when we apply that, apply this equation to our number, we pretty much just flip the 1's to 0's and the 0's to 1's, and that's your ones complement representation. In ones complement representation, as with sign magnitude, negative values are indicated by a 1 because that makes sense, right? Because if we had 0 in the front for our positive number, when we switch all the 1s to 0s and all the 0s to 1s, it becomes 1 in the front, and that says, hey, I'm a negative number. Okay? So complement systems are useful because they eliminate the need for subtraction. How do they do that? The difference of two values is found by adding the minuend to the complement of the subtraend. Okay, so here's how they do it. All right, so here's with ones complement addition. So we're going to find the sum of the positive 48 and negative 19. So here's how we represent positive 48. Okay. So that's 32 plus 16, right? And then here's negative 19. And how did they find negative 19? They wrote down positive 19, and then they switched all the 1s to 0s and all the 0s to 1s. And then you add them up. Okay. We note that 19 is binary, it's this number here, and so the 19 in one's complement is this number right here. You can see it right here. Okay, and then you add them. And this 1 at the end, do you see where they got this 1 at the end? The 1 was an overflow, and you add the overflow in. And so what is 48 minus 19 in decimal? Well, in any representation. What's 48 minus 19?
48 minus
Would be 39, right? And what is this number right here? Let's hope it's 39. Let's see, 2, that'd be 4 plus 8 plus 16, so that'd be 28. That'd be 29. Wait, did I write that right? 2, 4, 8, 16. Oh, 29. Dang it, I'm recording this. To skip that part. So it is 29. And note that that's what we got here at the end, was the number 29. So you could see that this ones complement does actually work. And adding two numbers at the hardware level is much easier than trying to borrow things. So this is why they went with the ones complement. Okay, so now when we want to store negative numbers in a computer, they decided, hey, ones complement works a lot better. So although the end carry around does add some complexity, one's complement is still simpler to implement than sign magnitude. But it still has one main disadvantage. It has two representations for 0, positive 0 and negative 0. What does negative 0 look like?
1, 1, 1, 1, 1.
Right, it'd be all ones. So if you had an 8-bit number, it'd be 8 ones in a row, and that would be negative 0. Because if you switched all the 1s to 0s, that would be 0. So they said, well, let's try 2's complement. And 2's complement solved the problem of having 2 zeros. Okay? And 2's complement is the radix complement of the binary numbering system. And the radix complement of a non-zero number n in base r with d digits is r to the dth power, or r to the d, minus n. But it's much easier than that. Okay. So to get a 2's complement of a number, first you get the 1's complement. And then you add 1. So in other words, you switch all the 1s to 0s and all the 0s to 1s. Then you add 1 to it, and that's your 2's complement. Pretty easy, right? So just flip all your 1s to 0s, all your 0s to 1s, and add 1 to them, and that's your 2's complement. And that's how a computer stores a negative number. So with 2's complement arithmetic, all we do is add our two binary numbers and just discard any carries emitting from the high order bit. So here's them doing the same sum 48 adding to negative 19 or subtracting 19 with 2's complement. Okay, so with 2's complement, the negative 19, first you take positive 19, switch all the ones to zeros, all the ones to zeros and zeros to ones. You add 1 to it. That's your 2's complement of negative 19. And then you just add it to positive 48. And you do actually end up with the correct answer. So that's how a computer stores your negative numbers, and that's how it performs addition, subtraction, multiplication, division. It uses this 2's complement. Okay, we don't go over the XSM representation. Okay, so this is an important little chart here. So let's compare our representations. So in decimal, how do we write the number 2? We write the number 2, that's pretty easy. In binary, how do we write the number 2? With 8 bits, we write it like this. Now just remember, for signed magnitude for a positive number, it looks the same way. And I think this is what always makes up students. The positive value, even in signed magnitude and 1's complement, look the same. It's only the negative number that changes. So the negative 2, okay, in signed magnitude, you would just put a 1 in front of it. And 1's complement, you would change all the 1's to zeros and zeros to 1's. And in 2's complement, you would add that 1. But do you see how the positive value looks the same? Okay, so number one thing out of this slide is just make sure that your positive numbers always look like regular binary numbers. And then your negative numbers, like negative 100 or negative 2, they're the ones that you change into their 2's complement. Well, actually your 2 is still a 2's complement, but you don't have to flip the 1's and zeros or zeros to 1's. It's your negative numbers represented in 2's complement that you flip the 1's to zeros, zeros to 1's, and add 1. Does that make sense? Maybe I should deviate a little bit right now. I want to make this chart for you guys. So there was a chart in your homework that you guys are responsible for creating. So in your homework, I assigned you number 27, and I think it's beneficial to kind of look at this chart together. So I thought we could kind of do this chart together today, and then when you guys have it for your homework, you could either remake it. Now in this chart, they show you the unsigned integer. This is a decimal representation, and they've only counted from 0 to 15, because if they counted beyond 15, it would make the chart like twice as large. Okay, so this is our unsigned integer. And remember that this unsigned integer I'm going to do it on Excel just because it's neater than me writing on the board. Alright, so notice that we're going to count to 15. And we're only going to count to 15, like I said, because then it would make our chart twice as big if we counted beyond 15. Now, how do we represent these things in binary? We should do this without even looking at the chart. So let's say inside of our chart they decided to use only 4 bits. And the reason we're only using 4 bits is we only need 4 bits to represent the numbers 0 through 15. Plus, it's a little bit easier to write. Okay, but note that the same thing would go for if we had 8 bits or 16 bits or 32 bits. Okay. So when we're representing these things, actually, maybe I'll represent them with these 4 rows. And the reason I'm doing this is so that I don't have to type so much. Okay. Now you might have noticed that when you count in binary, did you guys notice that when you count in binary, that first digit swaps back from 0 to 1 and 0 to 1, it goes back and forth. Did you guys notice that? When you're counting in binary, that first digit goes back and forth from 0 to 1. What did you notice about the second digit? It goes 0, 0, 1, 1. So when you're counting in binary, you can tell that that second digit goes from 0 to 0, 1 to 1. So it's fluctuating at half the speed. And did you notice that your third digit has 4 zeros and then 4 ones? And then your last digit fluctuates at half that speed. So then this digit you see, there's our binary numbers. Yes? So here's our, let's say, number 7. How do we represent number 7 in binary? It's 1, 1, 1. How do we represent the number 15 in binary? 1, 1, 1, 1. And you see that this is all the possible combinations of 4 bits. When we write our bits this way, when we fluctuate the right-hand bit 0, 1, 0, 1, 0, 1, and the second bit 0, 0, 1, 1, 0, 0, 1, 1, and the third bit we fluctuate at half that speed. We can represent all of the possibilities that these bits can be with each other, and those are all of our numbers. Okay, so there's all of our numbers for 4 bits from 0 to 15. And then in this chart, we're going to represent the signed magnitude of these bits. All right. So you guys can help me fill out this chart. What is 0 using signed magnitude? Actually, maybe that's the wrong question. What is this number in signed magnitude? That's the right answer.
0.
0, right. Okay, does everybody see? This will be our decimal representation of these numbers. We can represent this number in decimal right here. What number is this? If I were said, hey, this is signed magnitude, what number would this be? 1. That's pretty easy. How about this one? 2, 3, 4, 5, 6, 7. Now it's when we get here that this number is no longer going to be 8. Because we're using signed magnitude, that first bit no longer is a value bit, that's a sign bit. This is our values. This is the value 0 with a sign of negative. So this would be -0. Do you see how we have -0 here? In fact, I have to put quotations around him or else Excel changes him back. So that's our -0. What number would this guy be in one's our sign magnitude?
-2.
No. What number is this guy? 1, and then the one in front just tells him he's negative. So this guy's actually negative 1.
For the sheet on our homework, I thought they were wanting us to represent the unsigned integer as signed magnitude, not what it would be. Is that right?
I believe, well, yeah, you would just write it like this. You would say what number that this represents in signed magnitude. And you can write it in decimal, because I think that's the way we're used to thinking. You can either write it in words, or you can write it in normal decimal format. So note how we change a number from signed magnitude to regular decimal format. This would be the value of our number, the first 3 bits, or anything to the right of that sign bit. Remember, your first bit's your sign bit. So if this was 8 bits long, that first bit would still be your sign bit. And then the rest of the bits represent your value. So this would be 3, and this would make it a negative. Do you see how we're doing this? This would be the number 4, and then this would make it a negative. And this would be negative 5, negative 6, and negative 7. Okay. So note that with 4 bits, using signed magnitude, we only get to represent half of our values. You see how the other half of our values that we represented before inside of the computer are now representing negative values. So we no longer can represent the numbers 0 through 15. Using signed magnitude, our binary numbers now represent the numbers 0 through 7 and 0 through negative 7. We're just taking these binary numbers to represent something different to us. Does that make sense? And remember that the problem with using signed magnitude is that we had that carry, okay, and we had 2 zeros. And we had to carry. And carrying is hard inside of a computer at the hardware level. So then we decided to do 1's complement. Let's do 1's complement. So let's represent these things with 1's complement. So filling in our chart here. So if I wanted to represent, or I wanted to say, okay, this number here is now a 1's complement number, what number would that represent? Using 1's complement. So all the zeros to 1's, all the 1's to zeros.
1, 1, 1, 1.
Actually, sorry, I said that wrong. If it's a positive number, it stays the same. And when it's a negative number is when we switch the 1's to zeros, zeros to 1's, right? So in 1's complement, what number would that represent? Actually, it represents the number 0. Maybe it's hard to see this at first. This would represent still the number 1, and this would represent still the number 2. And actually, these numbers would all represent the same positive numbers. And that's what I was telling you about that one slide. Is that with your positive numbers, in signed magnitude, 1's complement, 2's complement, they actually all stay the same. Okay. It's when we get down here to negative numbers that we've now changed all the 1's to zeros, all the zeros to 1's. So what negative number would this guy represent? If I changed all the 1's to zeros and zeros to 1's, what number is that? It would be 0, 1, 1, 1.
7.
Yeah, it would be 7. So in 1's complement, this is the negative 7. This is how we write negative 7 in 1's complement. Okay. This is how we write, which number is that one? If we changed all the zeros to 1's and 1's to zeros, what number? Yeah, that would be negative 6. because it would be 0, 1, 1, 0. Okay, so this is how we represent negative 6 in the computer. Guess what this guy is? Negative 5, negative 4, negative 3, negative 2, negative 1. And if we change all the 1s to 0s, what number does this represent? Yeah, negative 0. Okay, so note that with 1's complement, addition is now easier because we don't have to carry anymore. Notice how we're adding, see how this kind of makes sense? When we add this number to this number, we're going to get that negative 7, and that makes sense that that would be the answer. So now with 1's complement, you can just add up a positive number and a negative number to do subtraction. But do you remember the problem with 1's complement? We had that carryover. Remember in our slides? I have to go back here. Remember we had that carry. Okay. So using 1's complement, you don't have to worry about this carry anymore. And then what was the other problem? So that was solved one problem, we don't have to carry. But what was the main problem now with 1's complement?
The negative 0.
Yeah, the negative 0. Actually, that was the main problem. All right. So let's look at 2's complement. Now this is how your computer actually stores things. It does use 2's complement. Copy these. Now with 2's complement, you change all the 1s to 0s and 0s to 1s, but then you add 1. Now you only do that for the negative numbers. This is the important part. Your positive numbers still represent the same numbers all the way across from sign magnitude 1's complement, 2's complement. This is still how you represent the number 7. It's only when you get to negative numbers that they now represent a different thing. All right. So what number does that number represent? 1, 0, 0, 0 and 2's complement. You figure it out. You change all your 1s to 0s and 0s to 1s, and then you add 1. So this is hard without the whiteboard, but it would be 0, 1, 1, 1 because it's actually 1, 0, 0, 0, right? But if I change all the 0s to 1s and 1s to 0s, I get 0, 1, 1, 1. Now add 1 to 0, 1, 1, 1. What do you get?
1, 0, 0, 0.
Yes, you get 1, 0, 0, 0. So I'm doing this math right here. I'm saying 0, 1, 1, 1 plus 1. Okay. And so it would be 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. And when you carry that 1 at the very end, that's what number you'll get. And what number is that?
8.
8. So this number here represents negative 8. Does that make sense? Here, we'll left align this. All right. So what number would this represent? 1, 0, 0, 1. If I changed all the 1s to 0s and 0s to 1s and added 1, you can do it on a piece of paper if you want, or I can do it right here. So if I took all my 0s to 1s, I would have 0, 1, 1, 0. And if I added 1 to him, what would I get? 0, 1, 1, 0, what would I get? What's 0 plus 1? 1. What's 1 plus 0? 1. What's 1 plus 0? 1. And do I have a carryover? No. So 0, 1, 1, 0 plus 1 is 0, 1, 1, 1. And what number is that? 7. So this guy represents negative 7. Guess what the next one's going to represent? Yeah, negative 6. And if you do the same thing, if you convert all the 1s to zeros and zeros to 1s and add 1, you will get the number 6. So that this guy represents negative 6. What do you think this number represents? Negative 5, negative 4, negative 3, negative 2, and then very importantly, what does this represent? Okay, make sure you understand this one. If I had all zeros, all ones, sorry. 1, 1, 1, 1. What's the ones complement of 1, 1, 1, 1? 0, 0, 0, 0. And if I add 1 to 0, 0, 0, 0, what do I get? 1. 0, 0, 0, 1, which is 1. So now this guy represents negative 1. So this is what that chart should look like. Hopefully it makes sense. So it shows you that in signed magnitude, 1's complement and 2's complement, your positive numbers always look the same. They're represented the same way. It's only when we get to the negative numbers that now we're representing things differently. So we're taking these 1s and 0s and we're just saying, okay, if I were to use signed magnitude in my computer, it would represent a negative 0. This number here, this binary number. If I were to use 1's complement in my computer, this would be the number negative 7. And in binary, if I were to say this is a 2's complement number, you would tell me that that's negative 8. And so 2's complement solves the problem of having 2 representations for 0. And it solves the problem of having negative numbers and having to carry. Okay, now when we have 2 negative numbers, or any type of negative number, we can add it to the positive number and not worry about the carry, and it'll work. You see how your computer can only do addition? At the hardware level, your computer can only do addition and it cannot use a carry. It does not worry about the carryover. Because it can represent negative numbers like this in 2's complement. So in your homework, you have to fill out this chart. Now in your homework, it does have the excess 7 as the last column. I say don't fill out that last column, okay? Because we don't have to cover excess 7 in here. So don't worry about the last column in your homework.
That's good because it actually gets it off.
Yeah. I cut it off, yeah, on purpose. So on the PDF that I uploaded for you guys, notice that I copied all the questions for you. I went ahead and cut off that last column because I don't require it. Okay? All right. But this chart's important. It's important that you understand. It's really easy, actually. Remember 1's complement, you just flip all the 1s to 0s, 0s to 1s. 2's complement, you flip all the 0s to 1s and 1s to 0s and you add 1. Okay? So I'm not going to upload this because I want you guys to write it out yourselves. But, okay. Now in your homework, I don't mind if you write it. Also, if you turn in handwritten work and you wrote on here, that's fine too. Okay? You don't have to do it on Excel on the computer like I did. I just did that so then I didn't have to write this giant chart on the board and it gets really messy if I do that. So I just wrote it in Excel. That's the most important thing today. I think the number one thing people get mixed up on is the positive number thing. So just very much remember that positive numbers are always represented the same way. It's only the negative numbers that we represent differently. All right, I think that's a good place to stop for our math part of our class today. So any questions on that? All right. Y'all kind of understand? And the more you think about this, the more you realize how it works. Okay? All right. And why it works the way it does. All right. So it's already 9. Now I know this is not an electronics class, and I don't expect you guys to be electronics experts, okay, but we are going to go over the basics of electricity, and we do have to know the basics of electricity. So I did get these electricity slides from an electronics book. Okay, I think they're pretty easy to understand. And we'll go up to, we don't really need to know the structure of an atom, but we should know the basics of electricity. All right. So even just up until a few years ago, chemistry was a required course for computer science. And why do you think chemistry would be a required course? Chemistry or physics was your choice. Now it's just physics. Now they require you just to have physics.
I'm guessing silicon and
Right. Because understanding electricity, you do have to know the chemical makeup of these components inside of your machine. Okay? So I don't go super in depth, okay, but we should know about electrons and protons a little bit to understand electricity. So we should know that all materials we know, including solids, liquids, and gases, contain 2 basic particles of electric charge, the electron and the proton. And the electron is the smallest particle of electric charge, and it's considered negative polarity. And the proton is the smallest particle of electric charge with positive polarity. Okay? The arrangement of electrons and protons in a substance determines its electrical characteristics. And if they're equal, then it's neutral and it doesn't have a charge. So to use the electrical forces associated with the negative and positive charges in matter, we have to separate the electrons and the protons. Changing this balance of forces produces evidence of electricity. Okay, and they show us a battery we're all familiar with. Okay. Electrons and protons in an atom assemble in specific combinations for a stable arrangement. And each stable combination makes one particular kind of atom. Such as, they gave us a hydrogen atom because he's the simplest atom to kind of look at. He has 1 electron going around 1 proton. Okay, so it's in balance. They cancel each other out. So these electrons, of course, are distributed in these orbital rings. And the distribution of electrons determines the atom's electrical stability. So these electrons in the orbital ring that are farthest from the nucleus are the important ones. They're the ones that are going to help us with electricity. If electrons in the outermost ring escape from the atom, they become free electrons. They're free. And they can move from one atom to the next. And this is what makes up electric current. Okay? So they give this kind of picture here. And they kind of show that, like, what is this, a copper? Yeah, copper has lots of electrons, and in its outer shell, there is 1 electron. Now, why do you think copper, looking at this picture, why do you think copper is a conductor? Do we use copper as a conductor of electricity? Copper
Yeah,
wire?
yeah, we do.
Yeah. Well, it's always getting stolen out of buildings, the copper wire. Okay? Because you pay money for this. Now, looking at this picture, why do you think copper is good for electricity?
It has a positive charge.
Yeah, it has this free electron here, way out here, right? He's 4 orbits out, and he's one little electron. You can see that electron could be a free electron and escape. Okay, it kind of makes sense that this atom here would be great for conducting electricity because of his electron in this outer shell. Okay. So when electrons in the outermost ring of an atom can move easily from one atom to the next, he's called a conductor. So we have copper as our conductors, we have silver, we have aluminum. How about gold? Gold is a conductor. Gold is used on motherboards. Okay. Gold is used in nanotechnology. So when electrons in the outermost ring of an atom don't move about easily, then they're an insulator. So if they hold on to their outermost electrons and they don't let them go and be free electrons, then they don't conduct electricity, like glass and plastic and rubber. Okay. And then of course semiconductors are materials that aren't very good at conductors and aren't very good insulators. We can force the outermost electron to move, but they're not so easily movable. And that's where we get our silicon and carbon. Okay, but what do we use to create computers? This is silicon. All right. The atomic number of an element is the number of protons in the nucleus of the atom balanced by an equal number of orbiting electrons. And the number of electrons in orbit around the nucleus of a neutral atom is equal to the number of protons in the nucleus. I don't really want to get into all this stuff. I think we just have to know that we have some free electrons. Okay. So we'll move on to voltage here. Now last class we were measuring our voltage inside of our Arduinos. And everybody measured voltages hopefully successfully. But remember, voltage is your potential. Your potential refers to the possibility of doing work. Any charge has the potential to do the work of moving another charge, so moving these electrons. Two unlike charges have a difference of potential. And a lot of times we write it PD, potential difference. And the volt is the unit of potential difference, and that's what voltage is. It's this ability for these electrons to move is your voltage. Okay. So the volt is a measure of the amount of work or energy needed to move an electron from positive to negative. So it's the ability to move these electrons to create a current. The metric unit of work of energy is called a joule. Okay, and they say 1 joule is equal to 0.7376 foot per pound. We don't really get into joules in here. And when the potential difference between two charges causes a third charge to move, the charge in motion is called your electric current. So current is a continuous flow of these electric charges. So it's electrons moving from one atom to the next from the positive to the negative charge. Or sorry, from the negative to the positive charge. Now when we write our currents, we usually write them with an arrow that goes from the positive to the negative, right? But if you think about the electrons are moving from the negative to the positive. So the actual current is moving in the or the electrons are moving in the opposite direction of what we usually label the current moving. Okay. So So here's a little picture that's kind of good to keep in your head. The potential difference across two ends of wire causes drift of free electrons throughout the wire to produce the electric current. So here's our negative, and here's our positive. Notice the electrons are moving from negative to positive. But when we write our circuit diagrams, a lot of times we'll write the current flowing from positive to negative. Though some circuit diagrams will write it from negative to positive. Okay? So this amount of current is dependent on the amount of voltage applied. So remember, your voltage is your potential difference. If you have more voltage, you're forcing more electrons to move, you're going to have more current. So the greater the amount of applied voltage, the greater number of free electrons, producing more charge in motion and a larger current. So more voltage equals larger current. And do you guys remember your Ohm's law? This is our most important one. V equals IR. So you can see, or you can even say I equals V divided by R. If voltage is larger, then your current's also going to be larger, right? So resistance is the opposition to the flow of current. You can't have current without resistance. And we measure our voltage in what's called ohms, which is this upside down horseshoe, which I think everybody knows by now. And resistance is usually labeled with an uppercase R. And then we saw how to take or view the resistance of our resistors with our multimeters last time. So just a couple more slides here. A circuit can be defined as a path for current flow. Any circuit has three characteristics. It has to have voltage. There has to be a complete path. It can't be broken. And the current path has resistance either to generate heat or limit the amount of current. When your current path is broken, it's called an open circuit. And when your current path has no resistance, it's called a short circuit. And short circuits can result in too much current, and they can... did anyone blow the fuse in their multimeter during a short circuit? No. That's good. I'm sure that will happen. So a closed circuit, this is like the simplest circuit that you could have. Notice it's one continuous circuit. Now, will current flow through this circuit? Does it follow all the rules for a circuit? What do you guys think? Do you think current's going to flow through this circuit? It says right there, current is flowing, so yes, it is flowing. And the reason it's flowing is because it follows all the rules for a circuit. It has a resistance, and it's closed. Okay, so remember that the PD, or potential difference, is our resistance, and that's what causes the current to flow from one side to the other of the battery. Okay, and this is how you would write this circuit in a circuit diagram. Here's our battery, and then here's our resistor. Here's our open circuit. Of course, is there no current flowing? Yes, there's no current flowing in this circuit. So like I said before, your electron flow is from your negative terminal to your positive terminal. What they call conventional current, they say it flows from your positive to your negative side. So when we write our currents, like on a circuit diagram, we usually draw the arrows from positive to negative. Okay. So they kind of show that here. So here's our conventional current, and then here's our actual electrons flowing from negative to positive, and then our conventional current we usually write from positive to negative. Now in this class, we're only going to deal with direct current. Does everybody know what alternating current is? Alternating current is like our plugs in the wall. And why would you want to stick a multimeter into the plug in the wall? Don't ever do that. Yeah. It can blow you up, okay? Yeah, don't ever stick a multimeter into a wall socket. Very bad idea. So it's a different type of current. It goes back and forth. It flows one way and then the other way. It flows one way and then the other way. Now, why would we want alternating current?
It's easier to transmit.
Yeah, it's easier to transmit longer distances, this alternating current. It's more efficient. Okay, but because it's reversing directions, it is more dangerous. And that's why with digital circuits, we just deal with direct current. Okay? And usually when we write digital current and alternating current is usually a waveform, because that's how it flows. It goes from positive to negative in a waveform. And when we write digital current, we usually just have a line. Okay, a straight line. And when, you know, we go down to the electronics lab and we look at our readers, we'll just see a line in here, not the alternating current. Alright. I think we're good. Is that good for everybody? We kind of understand electricity. I think this is a good time to break up. I'll go over these two slides on Thursday. So we did a little bit of math. We talked a little bit about electricity. I thought we could break up in our labs today and do some Arduinos. And the more you do this, the better you'll get at the multimeters and working with these components. So I thought we could just do some more labs from the text from that Arduino book. And so I uploaded Arduino Lab 2, Lab 3, and Lab 4. But I said you can work in programming pairs. So you can work with a partner or two. Just make sure you know you're helping and doing some of the building of the circuit. Make sure you switch off who's building the circuit. I said complete Lab 2, and then you have your choice of completing Lab 3 or 4, and you can complete both of them, I said, for extra credit.
Okay, so we'll do 2 after these.
And then in these labs, they do use programming. So you are going to program a little bit. So you can program these Arduinos. In the first lab you did not, in this lab you do. They show you the programming language. It's actually really very simple programming. Note that these computers have the Arduino IDE on them. Okay, you just start typing in Arduino and it looks like this. The programming language that the Arduino uses is a version of C, the C programming language, which makes sense for an embedded system like this to have the C programming language. I would hook up the Arduino first and then start the software. When you're typing in the programming language, you type it in just as you see it inside of the textbook. Okay. In fact, I'm just going to let you guys go for it today. And then we'll talk a little bit more about the programming language on Thursday, or the program that you guys write. Okay, but I'm just going to kind of let you guys go for it today. They'll figure it out. It's really not that difficult of programming. I bet you'll be able to read it no problem. And then we'll talk about it more on Thursday a little bit. All right? So let's see if we can